So this lesson, thankfully, is a little bit shorter. It's all about piecewise defined functions. So we have several graphs, 9 of them actually, that we want to know what does it look like just, on site. As soon as I see this is the shape that I'm thinking of, because we're going to take these basic functions and we're going to move them around. We're going to do transformations in one of the next videos. We're going to put pieces of them together here in this section. So that's what we're doing now, is finding, okay, what do these look like? What are some basic points that we can start with? And then we'll move from there to start moving them around and understanding them more as they get more complicated. So the constant function, the base points are down here at the bottom. This whole row is base points. So these would be the points that, if you're literally looking at the function f of x equals b, it's probably a constant value of some sort. So f of x equals like 4. We could plot that. It would be negative 1, 4, 0, 4, 1, 4, and 2, 4, right? So that's what we'd sub in. So I'm going to put b here. And we roll with it, right? Okay, the identity function is that y equals x line. So it's the diagonal one that I can kind of draw. And it goes through negative 1, 0, 0, right? It's the identity. Whatever the x is, the y is. The squared function, now we should start thinking, okay, these are getting a little bit more interesting. This is the parabola. 0, 0, negative 1, 1, 1, 1, 2, 4. Oh, I made it. Looks like a parabola, right? So we should be able to recognize that as an x squared function, and also when we see x squared, recognize that as a parabola, as that nice U shape. Okay. Now they get a little bit more interesting. X cubed has these base points. I guess I can write that in again. And it goes up and down. It is symmetric to the origin. Like we talked about before, it is odd. And has this shape. The square root function, though, now it doesn't have an endless domain in both directions, right? We can't take the square root of any negatives. So we start here and extend on that way. So that's the shape of the square root. That sometimes is a hard one to remember what it looks like and how it's supposed to be. So it can really help if you can put that into your head, that it's kind of a sideways parabola, right? I took the parabola and laid it on its side, and then we chopped off half of it so that it would be a nice function. The cubed root, though, it doesn't cause us any problems. We're allowed to take the cube root of any number. The cubed root of negative 8 is negative 2. That's allowed. So, whoops, we get a much more sideways looking graph for the cubed root function. All right, last 3. These are the most interesting ones. The reciprocal function, 1 over x, has asymptotes. We have a vertical asymptote, a line we cannot cross. We can approach and get closer and closer to, but never touch. And we have one on the x-axis as well. So this function looks like this. There we go. This is wrong. This point is negative 1/2, negative 2. We'll cover that. There we go. Sorry about that. The absolute value function, this one's the v. Most people can remember that for whatever reason. They think it's interesting. So this one comes out this way, looking like a v. And then the greatest integer function, this one's interesting. I don't love covering it because it's really not that useful, but there are times when we're going to chop off the decimal, right? There are times when we're just going to automatically round you up or automatically round you down. And so that's what this function does. And it kind of looks, it's called the stair-step function. It kind of looks like this. We are recording the greatest integer less than or equal to the number. So if we're at 0, we're at 0. And as we get closer and closer to 1, we're just chopping off the decimal. And when we get to 1, we jump up and go to 2, and then jump up and go to 3 and jump up, right? So we're just chopping off a decimal, basically saying, okay, whatever you were, 3.999 repeating becomes 3. So then the same thing happens on the left side, only when we get into negatives, it gets a little bit more complicated because the greatest integer less than or equal to it is actually the next bigger negative number. So negative 3.1 becomes negative 4 on the y. So that one's a little bit more interesting, but this does continue on forever and ever. And that's the stair-step function. Okay, so those are our 9 basic functions. We're going to start moving them around and knowing what they are and using them to apply to things. But first, piecewise defined functions. When we take a function and we define it by different equations based on different parts of its domain, that's considered a piecewise defined function. This usually applies in a situation where like the cost changes based on certain conditions, like if-then statements. But really anytime that the model is different for different parts of the domain. Think about modeling your height. As you grow from when you're an infant through your end of your growth years, right? You're not growing at a constant rate all the time. You grow and then you slow down, and then you grow and then you slow down, and then you grow and you slow down, right? You're generally trending upward, but it's not exact. And it changes how much you should be growing based on how old you are and what your biological sex is according to what they do for medicine right now. So that matters. And that changes, that model would change based on how old you are, how fast you're growing, and that kind of thing. So if we were trying to predict your height based on where you had been, we would need to use the fact that height should change based on your age, right? So the domain would matter, where in the domain we are. So that's what a piecewise defined function is. If we think about the absolute value function, that really actually is a piecewise defined function. It's x if x is positive, and it's the opposite of x. It's a negative x if x is negative. A couple of things to notice here. We have an equals to only in one place. This one does not have an equals. We cannot have two values for x that are the same, right? We can't do that. We can't use this, say 0 is this and 0 is that. That will make it not a function, right? So we have to make sure that if we're going to include this value in our domain, we only include it once and not try to include it multiple times. So the functions that you're given will obviously obey that rule, but when you make yours up, you'll definitely want to make sure that you're paying attention to only using or equals to on one side or the other of the number that you're using as that boundary. But this function here, this f of x, piecewise defined, would give us the absolute value graph that we have here. So it's the same thing. So they're generally not that straightforward. Couple of examples. Here's our function. Nice and big, it's got lots of pieces to it. But this helps us that they're all the same value, right? So that'll actually come into play as we go along. All right, we need to find f of -2, f of 0, and f of 3. F of -2 means we need to figure out where does -2 go into this, right? There's 3 here. -2 satisfies this x is less than 0. So we put it into here. So f of -2 becomes -2 squared, which equals 4. F of 0, that goes here. So then we get 2. I don't have to worry about what x is. Once I know which part of this it goes into, that's what I use. And then f of 3, that belongs here. That satisfies this part of the inequality that's greater than 0. So then we'll use this function. and do 2 times 3 plus 1. That would give us 7. So f of negative 2 is equal to 4, f of 0 is equal to 2, and f of 3 is equal to 7. Now we have some points, but maybe we don't need them. What's the domain of f of x? Okay, the best part of piecewise defined functions, because they are really complicated and hard, is that they give you the domain right there. It's just laid out for you. We're allowed to have x be anything less than 0, equal to 0, and anything greater than 0. Well, in a number line, we're allowed to be anything less than 0, we're allowed to equal 0, and we're allowed to be anything greater than 0. I've just covered the whole number line. So the domain is all reals. So that's the nicest part about it. You just have to figure out, okay, where does it start, where does it end? And if it covers everything in the middle, right, this is less than, this is equal to, and this is greater than, I've covered all of it, you're done. The nicest part about this, one way to help yourself do these is to create that number line. If you don't see it really well in your head, write it out. It's okay to draw that out. And I might even accept this as an answer for domain. I'd rather you wrote it out this way, with the domain being all reals. But it's not wrong to put in the number line. So use what makes sense to you. All right, now we want the intercepts. I'm going to erase some of these notations so we can actually read them. Okay, what are the intercepts of the function? Well, the y-intercept is 2, yeah? That's one of them. But then x could have intercepts too. So, to find x-intercepts, we do x squared equals 0, 2 equals 0, and 2x plus 1 equals 0. If we have all three of those, we set all three equal to 0 and solve for all three. This would mean x equals 0. This doesn't give us anything. And this would give us minus the 1 divided by 2, x equals negative 1/2. Okay, now we have to go back and check. Is 0 allowed for the x squared? Well, no, only if x is less than 0. So this turns out to not be an intercept because it didn't fit in that part of the domain. X equals negative 1/2. Well, the 2x plus 1 gave us that. Is that greater than 0? Again, no. So that's not an intercept either. So the only intercepts of the function is the y one at 0, 2. Now we get to graph it. Okay. For this, I think that one of the easiest ways to do this out, and the way that I organize myself to do this, is I make a table. Here's my x's and my y's, right? I'm going to pick values that are going to help me. Usually I'm going to pick the endpoints. Like if one of these said negative 3 is less than or equal to x less than 0, I would use the negative 3 as the starting point and 0 as the ending point. Because I don't have any endpoints, I'm going to just pick some. So I'm going to use negative 2 and 0. And that satisfies this first part, right? So I put a little line. I'll connect those two with the right shape and we'll be good to go. Then I need this second one. Well, the x value is 0 and the y value is 2. We knew that already. Okay. And then the third one, it needs to start at 0 and then it needs to go on bigger. I'll use 2 here. Okay. Now I just need to figure out the y values. If I put negative 2 into the function, I get 4 out. If I put 0 in, I would get 0 out. This one, it's an asterisk though, because I'm not allowed to equal 0, but I'm allowed to get super, super, super close to it, right? So I might not be able to graph 0, 0, but I would be able to graph something like 0.0000001 with its square, which would be super duper small. So I'm allowed to draw that point. I'm just going to put an open circle there so that we know we can't touch it, but we can get super close to it. Forgot to give myself axes here. Okay, so I need a point at 0, 0, but we have an asterisk so we know it's open. But I'm allowed to equal anything other than 0, so then I can plot my point negative 2, positive 4. And I'm allowed to go on past that, so I'm going to make this my quadratic. And there's the first part. Okay, this piece is done. Now I just have to plot the point 0, 2. There we go. Now that's done. Now the last piece, I forgot to get these x and y values. It has an asterisk at 0 again because we need to have that open circle. And we have 2x plus 1. So if I put in 0, I get 1. If I put in 2, I get 2 times 2 is 4 is 5. Just barely fit this. I've got my 0, 0. And at 2, I'm at 5. I'm allowed to go on past that. And this is a straight line. So there we go. So now we've almost done all of our first piecewise defined functions. There's one more part. Based on the graph that you drew, find the range. Remember that range is where we take the ruler and we slide it up and figure out, okay, where does it start touching and where does it stop touching the function? So, as we look at this, the absolute lowest y value is 0. But I'm not allowed to equal 0, so it needs a parenthesis. And then as we go up from there, really the x squared function covers everything else on to infinity, right? So, because it continues on, we're done. And that's our range. It's everything greater than 0. You could also write y is greater than 0. Note that I used y, right? When we're talking about range, we have to talk about y. So, let me go back just a little bit. When we're subbing in, we have to figure out which part of the domain that x value fits, and then sub it into that function, the one associated, or that equation, the one associated with that piece of the domain. The domain is given to us. It's written right out. We just have to figure out, okay, what's allowed. The intercepts, we're going to find the y-intercept by putting in 0. And then we're going to find the x-intercepts by setting each piece equal to 0, solving for x, and seeing if that's an allowable part of the domain. Graphing it, I strongly recommend picking points and plotting points so that you can have an idea of where this should be and where it should go. Because the x squared function should not show up on both sides. I can't have that happen. The x squared function needs to end at 0 with an open circle. So that's what we need to focus on, is having that graph properly. And so if you draw this out and you have an idea of what shapes these are, you'll manage to do this okay. And then find the range. I think you can do that from your graph. Note that when it says based on the graph find the range, even if you graph it wrong, you can still get that correct. Okay. So, your turn. Oh, I forgot to talk about continuous. Let's move this up a bit. 0 to infinity, 4, y greater than 0, is the function. What does continuous mean? Well, someone who goes on continuously goes on without end, right? Continuous means as you trace your function, do you ever have to lift up your pencil to go to somewhere else because you're not allowed to equal that? Well, in this case, yes, it doesn't all overlap, right? When I get to 0 coming in from the left side along the x squared, I stop at 0, have to jump up to 2, and then jump back to 1, right? Those jumps means it's not continuous. So that's a no. Fun fact, we get to talk more about continuous as we get very late in the course. All right, here's your next one. Try to do each piece. Find f of negative 2, f of 0, and f of 3. What's the domain? Remember, you should pause it here to be able to write some of this out. What are the intercepts? Remember how to find them. Graph it. Find the range. And is it continuous? So take a few moments to do all of that. And then when you come back, we'll show you the answers. Ray wants to know why I'm holding her this way. How'd you do? Most of it makes sense. Was it hard? It's weird to get through, but once you've done a couple, it'll make a little bit more sense. So check your work with what I have here. Make sure that f of -2 you got 1, f of 0 you got 3, f of 3 you got 0. You found that the domain was -2 on. My dog just found the cat. The intercepts, you should get 0, 3, and 3, 0. So the x-intercept is 3 and the y-intercept is 3. When you graphed it, you should have found that the points overlapped. So the point at 1 was at 4 for all 3 functions, all 3 equations. So you just kind of connected them. And I drew, you can kind of tell that I drew the big open circle here, and then I filled it in, and then I went on from there. So that just tells us that it is set up properly. It's okay for it to overlap like that. So then the range is everything 4 and lower, so including 4. And the function is continuous. I don't have to lift my pen up to keep tracing it if I wanted to. If any of that confused you, take another look. There's more examples that we can do. Write down your questions. You can send them to me in email. You can wait and ask me when you see me next. You can text me some way. Whatever works for you. But ask the questions, because you're not alone. Okay, so here we are at the end of the video. Pay close attention to what x values are allowed for each piece, right? I almost screwed myself up on the last one because I wanted to put f of 0 into the middle one, and it's not where it belongs. When x is 1, y is 4, but when x is 0, I have to put it into the x plus 3 function. So pay close attention to that. Know the shape of the graph for the section you're drawing, right? When we drew the parabola, we wanted to make sure it looked kind of curved so that we can see that this is, part of a parabola and not just a straight line going off that way. And it really will help to plot points and connect your dots. So, that's it for now.